Well, it's a great pleasure to be here, to be back in Edinburgh. And I'm just reflecting, I say that every few years, but this time it is a true pleasure because the sun's shining and I've met lots of old friends. It's always a pleasure, but a particular pleasure to be invited by you to speak today. So what I'm going to do is to give you my most difficult talk, out of respect. It deals with stuff that we've been doing for the past couple of years on active inference and tries to take that approach to the brain, cognition, as far as we can in understanding things like insight, curiosity, mindfulness. So I'm giving you an apology at the beginning that this is difficult material. I'm going to have to do it within 45 minutes, and I'm not going to, so someone's going to have to tell me to shut up at 45 minutes. If we don't get to the end, don't worry. This is all for fun. We're not going to be talking about predictive coding. We're actually going to be talking about the equivalent, the sister of predictive coding for models of the world that can be cast in terms of discrete states. So we're going to be talking about Markov decision processes of the sort that you might find useful in modeling psychophysical or psychological or indeed economic, like game paradigms. And that's going to help us a lot in understanding the role of various mathematical formalisms that drive good behavior. So let me just overview my talk for you. Let's actually get to know each other. And we'll do that through playing a game. And the notion of this game is for me to find out how Bayes optimal you are. Yeah? So I'm going to judge your optimality on your performance collectively on this game. So here's the game. I have a purpose, and I'll explain why after we do the game. But in prosecuting this game, doing this experiment with you, I'm after one number. It's basically how many exposures do you need to discover the abstract rule that lies behind this game. So here's the rule. I'm going to tell you your prior beliefs. There are going to be three colours presented, and those colours are the large circles here, green, blue, and a red. For the moment, ignore these little circles down here. And your job, your task, is to choose and to tell me and your friends the correct colour. And all that I will tell you is that the location of the correct colour depends upon the colour of the middle or upper dot here. So that's all you know. And all I'm going to tell you is whether you are right or wrong in making choices. And I repeat, what we're after here is how many trials of this game does it require for a Bayes optimal Edinburgh audience of intelligentsia to discover the rule. I'll tell you how UCL did once we find out how well you did. Okay, so let's start the game then. Andy, what colour would you like? What's the correct colour? Green. Okay, so we're focusing on the first trial, and Andy has chosen green, and the correct colour is indicated by this magenta ring here. He was absolutely right. Well done, sir. I don't know how you did that. Special powers. Okay, would you like another go? No. You can choose somebody else. David, what would you like?
I'll go green.
You're going to go with green. Well, sir. Are you a philosopher as well?
I guess I am.
You, sir, what would you like?
Red.
You want red. This is remarkable. Okay, this doesn't normally happen. I'm not sure it's going to confound the rules. Well, yes, precisely. I shouldn't have started with this, should I? You, sir, what would you like?
Blue.
You'll go blue.
No!
Oh.
Where are you from?
Glasgow? Okay, well, that's good. That's a prediction. That's a violation. You'll learn something now. So you had a hypothesis. It didn't work. Now learn from that. Okay. Lexa. Well done. Did you have a reason for choosing that? Could you tell me what that reason was? No, you meant as soon as you think you know the answer, you should shout out. That's the number I'm after. Well, isn't that amazing? Okay, Edinburgh wins hands down. All right, so let's remember that number. 1, 2, 3, 4, 5. You had 5 exemplars, and you've discovered the correct abstract rule underlying this game with 5 exposures. All right? I mean, I know you all didn't. Put your hand up if you also discovered that, but were too shy to say so. Loads of people, yes. Right, can you remember that number? So what we're going to do now for the rest of the talk is to build a theoretical formalism that will allow us to simulate a little agent who plays that game and tries to discover the rule and see how well they perform in relation to you, the audience, or in particular, Alexa here. So just to make sure that we've all understood the rule, what's the colour of the next one? Green is at the centre, and that means the correct colour is? Shout out, I can't hear. Blue said blue, no. You got the correct rule. Shall I just rehearse your rule? If the colour in the centre is green, then the correct colour is in the centre, which is always green. If the colour in the centre is blue, then the correct colour is always on the right-hand side. And if the colour is red, then the correct colour is always on the left-hand side. So what would we anticipate that the next colour is going to be? It's green, yeah. And the next one, so we have blue. Red, yes. Red. Red, yeah, good. I'm going to play the game again just to make sure you've remembered it. You're undermining my confidence that you generally remembered the rule that you saw now. However, you did articulate it on exposure number 5. Right. So, and those are the rest of the answers. So, I repeat, the objective now is to see if using purely Bayesian principles we can reproduce that remarkable ability to gain insights into the structure, the causal structure of our world with a sparse number, very, very sparse number of bits of information or evidence. And the route we're going to take is through active inference and Hamilton's principle of least action, the path of least resistance. I'm going to talk about that from the point of view of choosing optimal behaviours, how that rests upon the resolution of uncertainty and surprise and predictions that create surprise, namely generative models. I'm going to briefly talk about the sorts of process theories that follow from this if you're a neurophysiologist. So by process theory, I mean a theory of neuronal processes that does this abstract Bayesian inference, and in this example, this insight into the rules that, or contingencies that govern our sensory inputs. Make some brief comments using simulations about the sorts of empirical predictions you would occur, but then I want to come back to that task and simulate that task and compare the performance of a Bayes optimal agent with you, and we're going to find some peculiar discrepancies, and then we're going to try and explain those discrepancies. But let's start from the beginning. The way I normally start this talk is by asking the question, so this is all about how do I select the best next thing to do? So imagine you're an owl and that you're hungry and you're flying around. What are you going to do? You, sir. You're going to look and search. Perfect answer, thank you very much. So that's exactly what you're going to do. The first thing you're going to do, you're going to fly around and you're going to look for your prey. You're going to locate your prey. In my rhetoric, you're going to resolve uncertainty about the location of the prey before you engage in predatory or exploitative behaviour. That simple example tells us quite a lot, in fact, a lot of fundamental things about the mathematics that you would bring to the table to try and explain or describe that sort of behaviour. And I'm going to compare and contrast two approaches with which some of you might be familiar. On the one hand, I'm going to talk about optimal control, reinforcement learning, value maximization under the general umbrella of selecting actions U at any point in time that maximize some value function of the states that would ensue if I took this action now. So I take action U now, then there will be some state that I realize in the next time step that has a value, and my job is to select those actions that maximize a value function of states. And I'm deliberately going to introduce this dialectic between the alternative formulation on this side. I'll in fact dissolve the dialectic later on, but I want to celebrate it at the moment just to make a few key points. The alternative formulation says, well, hang on a second, we've just said that the first thing we do with any problem is resolve uncertainty, and we go and forage for information, we go and make sure that we know the context, resolve our uncertainty about the consequences of any subsequent action. Now, things like uncertainty are attributes of beliefs, which means that we know that the best action cannot be a function of states of the world, even if they're fictive. It has to be a function of beliefs about states of the world. In other words, a function of a function, known mathematically as a functional. So what we're saying is, no, this doesn't work. We have to be able to cast the solution in terms of optimizing an energy functional of a belief under a particular course of action. But we've also just spoken about looking for the prey and then eating the prey. Implicit in that is that the order matters, right? It matters whether I first go to the fridge and then take out something to drink, or whether I start drinking and then go to the fridge. They will have very, very different consequences. So it's not just a question of selecting the best next action. It's selecting the best course of actions or sequence of actions that I'm going to refer to as a policy. And which means then that we have to optimize our policies, not our actions, our sequences of actions, which means that we're now optimizing a path integral or a time average of an energy functional of beliefs about states in the future S sub tau. And that's nice because that quantity, a time integral or a path integral of an energy, is called action, which means that all that we are saying is that we can understand good behavior in terms of Hamilton's principle of least action. And this should be contrasted with what you would normally be exposed to if you do reinforcement learning, optimal control theory and the like, which appeals to a very different principle called Bellman's optimality principle. So that would entail things like optimal control theory, direct programming, reinforcement learning, expected utility theory, and so on and so forth. The alternative that is epistemically invested in virtue of optimizing a functional of beliefs are the free energy principle, active inference, and what we'll see later as artificial curiosity, referred to in robotics as intrinsic motivation, Bayesian decision theory, and so forth. That's the formalism I'm going to use. There's an interesting physics backstory as to what energy functional one should choose. I'm actually just going to say up front it's going to be the variational free energy, and I'll try and motivate that post hoc by showing that it has an enormous amount of construct validity in relation to things that you will recognize. One of these different ways of unpacking this free energy functional, I'm sure that you will recognize, whoever you are or whichever department you come from. Don't worry about the equations so much. You treat them as iconic descriptions of the sorts of quantities that go into and lend this functional its names. And by rearranging these quantities, we can recover things that most people will realize or recognize. So what I'm saying is that we can prescribe good behavior in terms of prior beliefs that I will follow a policy pi, ignore this constant proportionality at the moment, it's going to play the role of a precision parameter, that is inversely proportional to the expected free energy, where this is a Hamiltonian action or an average free energy associated with any policy over time, where the goodness of a policy is a negative free energy, and it has this form here. Again, don't worry about the mass. All this is saying is that this is an energy term, and this is an entropy term, and the difference is a free energy. What I do want to worry about, though, is different ways of writing down these things. These are probability distributions over states of the world that cause observable outcomes under particular policies. Pi and Q are our beliefs about the states of the world, and P corresponds to our model of, or the process generating outcomes from causes or states of the world. And by fiddling around with this equation, one can write it down in a number of different ways, which I think are very enlightening. This is probably one of the best ways in which to understand how to unpack this equation. And what it's done, or what I've done here, is essentially split it into two bits. I've split it into something called extrinsic value, which basically just says, I expect my actions to maximize the probability of preferred outcomes, minimize my surprise about my prior preferences about outcomes in the future. And that's going to play the role of an extrinsic value, where the extrinsic part comes from the having these prior beliefs about outcomes, just given I am me. And the other part, what's left over, plays the role of an epistemic value, an information gain that resolves uncertainty. So it scores the degree to which my uncertainty about states of the world will be reduced if I pursue this policy. And this is the intrinsic motivation or intrinsic value that we've just mentioned. It is also, if I now just forget about the extrinsic value here and just focus on this term, this expected KL divergence is exactly the same as the Bayesian surprise used by people like Christoph Koch and Etienne Boldi to score visual salience. So they associate visual salience, namely, where would I look next to get the most information gain, to resolve as much uncertainty about the causes of the visual impressions that I could possibly solicit or sample. The salience is the Bayesian surprise, the degree to which I update my prior beliefs to make them into posterior beliefs, and the greater the difference, the more updating and information gain I have observed. That mathematically is actually also something much simpler. It's simply the mutual information between causes and consequences, the states and the outcomes. It's just the mutual information. And the notion that we act to maximize mutual information has a long pedigree. I put Horace Barlow here just to represent his views on the early versions of the Infermax principle, maximum efficiency, minimum redundancy, encoding in the visual system. The same principles in play here. Maximize the dependence of the mutual information, namely the information gain between causes and consequences. So that's one nice, purely epistemic view of this energy functional. I'm now going to put this quantity back in play, and I'm going to take out uncertainty about the consequences of observations, in the sense that I'm going to assume that if I observe something, I know its true state. So I'm taking away any ambiguity about my observations. If I see something, that's the state of the world. If I take this term away, I'm left with these two terms, where states and outcomes become the same thing. And what we have here is the objective function used in the most advanced forms of optimal control in engineering. It's the KL divergence, or the difference between what I believe will happen under a particular policy and what I want to happen, or my prior preferences about the long-term outcomes. So this is KL control. In economics, it comes along as risk-sensitive control or risk-sensitive behaviour. So that's in the absence of any ambiguity. I can go even further and prune this equation a little bit more and take out any risk. So I know exactly what will happen if I do this, and that just leaves me now with expected utility theory. So we're back to this extrinsic value here. So I will choose the policy that maximizes the probability of my preferred outcomes, and I can now treat this log probability as an extrinsic value or a utility, a subjective utility. And just for fun, we can take out both risk and ambiguity, risk and intrinsic value, and we're just left with this term here, which is James's maximum entropy principle. And what this basically says, if I have no preferences at all about outcomes in the future, then my best bet is to keep all my options open and disperse the probability over outcomes as much as possible. So essentially keeping options open. So to realize those sorts of imperatives that are offered by minimizing this free energy functional, we have to have this model, this probability structure that relates causes to consequences and how those consequences unfold under different behaviors or actions. Again, this is the last detailed mathematical slide, but don't worry about the equations. I'm going to be able to portray the simplicity of this, the sorts of models we're going to use to demonstrate that abstract rule learning task using the graphics on the right-hand side. So these models are Markov decision process models that are about as simple as you can get in terms of describing worlds. And all they say is that we have some state of the world that evolves to produce another state, that evolves to produce another state, and at each point in time, the state of the world determines observable outcomes. And the probability of an outcome given the state is governed by a likelihood matrix A. So it's a probability of an outcome given a particular state. And the transitions, the Markovian aspect of this, are encoded by a probability transition matrix B, which simply says, given the state of the world was like this at the previous time point, the probability that it will be in this state at this time point corresponds to the element of this transition matrix B. But crucially, these transition matrices, the way that the world unfolds, depends upon what I do. So for every policy, every sequence of actions I take, I will have a set of B matrices, which means that now I have to have beliefs about my policies. And if you remember before, I said to ignore this gamma parameter. I don't want to focus on it too much, but just for completeness, because we've now cast the problem as an inference problem, planning as inference, because we've now created a generative model where outcomes are generated by random variables like hidden states, but also, crucially, hidden policies, random variables that I have to infer. I have beliefs about what I am doing, and those beliefs have a precision or an inverse temperature, which we'll call gamma, and I actually have prior beliefs about that precision. We'll see later that this looks very much like the sorts of quantities that are encoded by dopaminergic discharges in the brain. And then finally, our preferences will describe in terms of these log prior preferences or cost functions, C here. So with a very simple parameterization, A, B, and C, we have the machinery to build a generative model of almost any sort of process, any sort of game, or any sort of paradigm that we want to consider. And all we have to do, so this just writes down this generative model here. We have to specify the form of our posterior beliefs. We build into this what's called a mean field approximation. That's why this is going to be called belief propagation or approximate variational Bayesian inference. That's not so important here, but just to reiterate, we will be assuming some simplified forms for the posterior beliefs, and in so doing, we can now just write down the optimal values that these posterior beliefs should have in order to minimize this action or path integral that I unpacked on the previous slide. And the solutions to that minimization problem under this particular form for the approximate posterior are remarkably simple. And furthermore, they look very much like the sorts of equations that you'd see in computational neuroscience. So let me just take you through them very briefly. Remember, in this world, there are only three sorts of unknown things. There's the hidden states of the world, there's a policy I'm pursuing, and my confidence about that policy, namely the precision. So there's three things I have to optimize. And the optimal value are the expectations of those three sorts of things that minimize this variational free energy or log evidence bound. And it turns out that the best states of the world are just a sigmoid softmax function of linear mixtures of outcomes, this is a likelihood term, and these empirical priors that come from the past and the future, mediated by my beliefs about transitions. The action selection, namely inference about the most likely policy I am pursuing, is just a softmax, a standard softmax response rule of the goodness or the negative goodness of a policy multiplied by its inverse temperature here, or sensitivity or precision, where that is 1 over beta, and beta effectively is like an expected utility prediction error, the difference in the goodness or the negative goodness of outcomes or the policy with and without knowledge of the past. That's what the pi and pi sub naught gives. Again, I don't want to focus on that. That has nice connections with the reward prediction error literature. I really want to focus on these equations here, inferring the states of the world and inferring what I am doing and what I should be doing. And if I can infer what my policy is, then I know what to do next. So if I average over all my policies in proportion to the likelihood I'm pursuing that policy, that has all my epistemic and utilitarian bits in it, then I can select the action that realizes the outcomes that will be pursued under that policy. And that's what this little panel says here. So this is a very rough schematic that just associates the update equation, the Bayesian belief updates here that we get from minimizing variational free energy under that generative model to different bits of the brain. This is probably better exemplified in this schematic here. So the basic idea is that we get these observed outcomes, this sensory input, comes into the brain. We do our state estimation by optimizing our beliefs about hidden states of the world under all plausible policies. This allows me, or the agent, to evaluate the goodness of the policies in terms of the expected free energy that I will encounter should I pursue that policy into the future. I can compute the precision or the confidence in those beliefs and generate a probability distribution over all plausible policies. And I can use that probability over competing policies to weight or average the next state. And if I know the next state, I can select the action that brings about or realizes that state. I can act, I can solicit another outcome from the world, and then the cycle begins again. So we have this sort of perception-action cycle in play that is informed with this deep generative model that is deep in time because it considers outcomes in the past and in the future. So that's the basic idea. I'll show you one simple example of this and then come back to our abstract rule learning task. So the illustration here is a very simple task. It's a two-arm maze, and this rat believes it's got two moves in which to secure a reward in one of two baited upper arms of the maze. And it can, and if it secures or goes to one of the two arms, it has to stay there, so it can make a mistake. Crucially, though, there's an epistemic option. It can go to the lower arm of the maze where it will find a cue, an instructional cue. And if it's blue, it means the reward is on the left-hand side, and if it's green, it means the reward is on the right-hand side. So it's got a choice. It can either go directly to one of the two rewarding arms, and 50% of the time it will be correct in a 50% rewarding schedule, but if it's wrong, it loses the opportunity to go and subsequently get the reward. Or it can forego one move without reward to go and act epistemically to explore, to resolve uncertainty about where the reward is, and once it knows where the reward is, it can then just go to the rewarding arm. So exactly the same expected utility, but from the point of view of the free energy function of beliefs, the epistemic drive is much more attractive. So what will hopefully happen is that the agent, in minimizing expected free energy, will resolve its uncertainty and then go to the baited arm. This just details the way that you build these state spaces. It's an interesting game. very quickly. You have to specify the control states, which are just moving to any of the 4 locations. Hidden states of the world. Here there are 2 factors: where am I, and the context of the reward on the left or the right, and then how these hidden factors or hidden states conspire to produce outcomes. Outcomes, for example, I'm happy, I'm here, and there is a reward there, or I'm not so happy, and there isn't a reward there. And the happiness is scored in terms of this cost function or log preference in terms of natural units or nats, if we're using natural logarithms, which we are here. So this is basically specifying the utility, if you like, that complements the epistemic part of the free energy in driving behaviour. So that's the setup. This is the sort of behaviour you get. The top panel scores the initial state and policy selection. The lines here reflect confidence about the final confidence about the policy being pursued. It can make 2 moves or 4 moves, so there are 12 there are 10 or 12 options, sequences of moves it can make. This scores the final outcome and the integrated expected utility and reaction times. This here scores its beliefs about the beginning of the trial, the context, is it right or is it left, that has been accumulated through learning by minimising this free energy functional over time. These 2 middle panels we'll come back to. These speak to the process theory, so we'll come back to those in a second. I just want to illustrate the basic sort of behaviour which you see in any of these sorts of simulations. And what I've done here is start off by placing the reward on the left and the right and the left and the right, and then after a couple of trials I've just kept it in one place. So now the rat could learn that in fact the reward is systematically on one side. And what happens is, in this sort of situation, is that the rat starts off by going to resolve its uncertainty, acting epistemically, and then going straight to the reward, and it's happy. After a while, though, it starts to accumulate evidence that, in fact, that's an unnecessarily explorative behaviour, and that, in fact, the information gain obtained by securing the instructional cue starts to become less and less and less, because it starts off more confident that the reward context is going to be a left context. And that means as the epistemic part of the free energy goes down, at some point it falls below the extrinsic value or the expected utility, and suddenly exploitative behaviour kicks in. And at that point we see a transition in behaviour, and suddenly the rat will go straight to the reward. And this transition here is mediated simply by this reduction of uncertainty, in this instance, in terms of accumulating the parameters that encode the initial beliefs about the context. So that's a nice model of exploration-exploitation trade-off, all underwritten by variational principles and information theory. How does it help understand the sorts of phenomena that we might see if we're animal electrophysiologists or indeed animal psychologists? Well, I'm going to go through this quickly because I want to get to the return to the game that we were playing at the beginning. But just to give you a taste of what you can do, what we have to do is to convert this normative framework into a process theory. And it's actually very easy to do. What we do is we take these solutions that we talked about before that underlie Bayesian belief updating, that are the minimizers of this free energy functional. And instead of explicitly working out the solutions, we're just going to write down a gradient descent or a hill descending scheme such that the rate of change of any of these variables is proportional to the negative gradient. And then the system will inevitably find the minimum. And if we do that, the equations don't change very much. If you keep your eye on the equations here, we get this, where a little dot has occurred or appeared on the top there. There it is there. And it's balanced with this decay term here. What I've just essentially done is convert that solution into a differential equation, and in so doing, now I've got a model of neuronal dynamics that, in fact, are probably better exemplified in this slide here, where we can now fill in these panels that describe the updates of the hidden states and the updates of our confidence or precision in beliefs about behaviour. So again, 3 unknowns, hidden states driven by observations, beliefs about the past and the future with the decay term, that have all the look and feel of changes in transmembrane potential that are passed through a sigmoid voltage current activation function to create a model of neuron firing. Here we have our policy selection and the learning, which I talked about before in terms of the context. Again, has all the look and feel of associative plasticity with associative terms here and decay terms here, which means now we can start to simulate electrophysiological responses in terms of little ERPs and look at the differences between our explorative and exploitative periods of behaviour. And we can even simulate dopamine-like responses that have this sort of characteristic phasic behaviour that is due to and only to the changes in the confidence that this animal has about the context in which it's operating. With that sort of model in mind, you can do all sorts of interesting things. I've just focused here on a couple of trials. Here are the neural firing rates of various cells encoding expectations about different states of the world at the beginning, second and final move of the rat, at the beginning of the trial, at the second point in real time of the trial, and the end. And we can track the expectations about the finally chosen option in relation to the unchosen option, showing characteristic evidence accumulation with a degree of saltatory dynamics here as there are updates to the beliefs as new evidence or sensory information is acquired. As time goes on, the rat gets more confident, it's more efficient, and these simulated electrophysiological results show something called phase precession. If we assume that the evidence acquired, like visual sampling, is acquired every, say, 250 milliseconds, we get things like theta-gamma phase coupling and phase precession, and we can even simulate dopaminergic responses. We can simulate place field responses. I like this example because it highlights this sort of the temporal thickness that comes along with these generative models with future in mind. So I said before that these states at the beginning, middle and end of the trial, at the beginning of the trial, at the middle of the trial, and at the end of the trial, which basically means that neuronal representations that start off being beliefs about the future become beliefs about the past as time progresses, which means that you've now got a spatio-temporal encoding of trajectories as you navigate through spaces that lends the dynamics that you would see, the sort of flavour that you get when you look at things like place cells and grid cells and the like. You can do violation experiments. Very quickly, an example here. I've just shown the simulated electrophysiology for 2 trials at the beginning and just prior to the transition. So the stimuli and the behaviour are exactly the same. But here, the agent is much more familiar with outcomes, so that we can treat these as a standard, whereas everything's surprising at the beginning, and we can treat that as an oddball. And we can see the decrease in simulated electrophysiological responses, usually associated with things like the mismatch negativity. And in terms of the confidence, the agent is more confident now, and that increase in confidence actually emerges earlier, showing a simulated transfer of dopaminergic responses from the rewarding cue to the instructional cue, resolving the uncertainty. Good. I went through that rather breathlessly because I'm mindful of my 45-minute time constraint. So I want to get back to the game. Right, you all remember the game? So if I, right, you're looking at me cheekily. Right, what's the first colour on the first slide?
Green.
Perfect. And the next one. Remember, the green at the top means green is the correct colour because it's centre. Blue at the top means that the correct colour is on the right-hand side, and red at the top means the correct colour is on the left-hand side. And you discovered that rule, if you remember, after 1, 2, 3, 4, 5 exposures, which I repeat is remarkable. I've never seen that before. 7 is the current record, and that was in Zurich. Right, so we're now going to use exactly the same equations that I've just shown you. I'm not sure that I will show you this, but you can actually simulate EEG responses and eye movements and the like whilst doing that paradigm. Now, clearly, we're not going to be able to tell our agents what I told you, but we can write in through the prior beliefs about the likelihoods and through their preferences. Basically, I can tell the agent what I told you. So what I've told the agent, or what the agent knows, is that there are 3 rules. There are 3 correct colours. The hidden states of the world can be where I'm currently looking. And my decision, I could have chosen one of the 3 colours or declared it, or I can be as yet undecided. The outcomes are basically what I'm currently seeing, which is red, green, or blue, or if I'm at the starting location in the centre, then I see nothing. Where I'm actually looking, and I'm feeding that directly back to the agent, and some feedback. If I haven't decided, it's open, I can be right or wrong. Crucially, I'm only going to give preferences about being wrong. So I'm just going to penalise being wrong, and everything else that's quite sufficient to model this sort of trying to get the rule right just by disclosing, resolving uncertainty. But here's the important bit. So the rule, all the heavy lifting in these sorts of problems is in the relationship between hidden states, latent states of the world, and what happens. So it's in this likelihood mapping between latent states and observations that initially the agent doesn't know. And if the agent knew the rule, then they would know exactly the combination of hidden states that would enable them to identify the correct colour and thereby predict a good or a correct outcome. So, for example, I've just presented this rather complicated, it's a high-dimensional matrix mapping from all the different hidden states of the world to the outcome. Again, it's not necessary to understand this in detail, but in brief, this is a tile, a 3x3 tile of little contingency or likelihood matrices. And this is the actual way that the rule works. So if we're looking at the centre, then so this is looking at the centre, this is sampling the left, and this is sampling the right. And this is the correct colour, the hidden state with the correct colour, and this is what I would see. So only when the rule is left, which means that if I were looking at the centre, I would see red, would the correct colour be disclosed by sampling the left. Otherwise, all bets are off and it's a uniform probability. So it's this structure in this contingency or likelihood matrix that embodies the rule. This is what the agent started with. It has no concept of the rule, other than it knows the centre colour is, if it looks at the centre, it knows which rule's in play. But it doesn't know what the rule means, exactly like you didn't know what the rule was. You knew there was a rule there, you knew how to identify it, but you didn't know what it meant. So it's now equipped it with exactly the same knowledge that you had, and now we're going to expose it to exactly the same sequence of events that you saw in going through those trials in the previous slide. And I'm showing this, sorry, I've forgotten I got this bit here. There is another equation here. What we're going to illustrate with this particular behaviour, let me show the behaviour first, and then I'll come back and explain why I wanted to show that slide. What we're going to see here is that after a period of time, using the same formalism to describe the behaviour in terms of beliefs about policies I should be pursuing, initial outcomes and initial states and final outcomes. Here I'm summarising the belief updating in terms of the free energy and the confidence about behaviour. And the reason I'm doing that is to show that in that particular game, with those particular stimuli, this Bayes optimal agent was able to effectively infer what was going on by accumulating evidence in its A matrix about contingencies, to the extent that after 13, 14 trials, it was pretty confident about what was going to happen and what it was going to do, at which point the free energy is suppressed, at which point its prediction or behaviour is 100% perfect. I must confess, this agent actually was allowed to choose again when it got it wrong, which is why the performance looks better than your performance. Well, with the exception of the first three answers from the philosophy department. So the red squares are mistakes, but there will be more first mistakes if I put the first mistakes on. So it can do this. It can learn the rule. It can accumulate outcomes by just basically adding counts to this sort of matrix mapping from hidden states to outcomes. And it can learn implicitly the underlying rule and behave properly in relation to its prior beliefs in exactly the same way that you behave properly in responding to my task instructions. The interesting bit about this behaviour, though, is the way that it deliberately goes and searches for information that will resolve its uncertainty about this mapping between states and outcomes. So this is not quite the same as disclosing hidden states of the world, like when the rat was looking for the blue sign to tell it that the reward was on the left. This is a bit more subtle, and that's where this equation comes in. Previously, we've been talking about intrinsic and extrinsic value in terms of the reduction about uncertainty pertaining to the states of the world, and the extrinsic value being our utility or our preferences, that actually can be arranged into risk and ambiguity. But there's another set of unknowns that's crept in here. I've introduced it. Those are the parameters of the likelihood mapping that entail the rule. So these are not states of the world. These are contingencies, parameters of the generative model. But exactly the same rules apply. There is an intrinsic value to policies that resolve uncertainty not about outcomes or hidden states, but about parameters and structure of the world. In other words, there's an attractiveness to putting yourself in situations to find out what happens. So it's just like novelty. The novel situations afford the opportunity for you to reduce your ignorance or your uncertainty about what would happen if I did that. That becomes intrinsically attractive. And that intrinsic novelty-seeking, uncertainty-reducing behaviour is what's been exploited by this Bayes optimal agent that can solve the problem in just 12 moves. And we see that illustrated in this panel. Again, I don't want to spend too much time on it, just to highlight the result. The key result, these are the beliefs about hidden, about policies or behaviours, particularly where I'm going to look, at the first trial and at a trial after it has realised or learned the rule. And the crucial thing here, it goes to the centre location, but then finds the other two locations equally attractive because they're novel, because it doesn't know what would happen if it looked at those two regions. Not because of the hidden state of the world, but the implications for the overall structure. What's the correct colour? What's the consequences of declaring red? But at the end, this exploratory drive, this attractive novelty of situations that it doesn't know, has just gone away, and it just basically goes straight for the location that contains the correct colour. So here the utility is supervened because there's no more novelty left. So by learning the rule, it's destroyed novelty. There is no novelty left. There's no epistemic attractiveness in securing information that will make it a more experienced navigator of this particular task. The electrophysiological correlates here are interesting. I won't dwell upon them. These are the simulated ERPs for those two trials before and after the rule learning. The interesting thing is that once it knows the meaning of outcomes, then you get simulated ERPs, which are much more pronounced, shorter latency and higher amplitude than when it doesn't know the meaning of stuff. So you make some very clear predictions about before and after insight in terms of the electrophysiological correlates. And that was highlighted here. However, I want to close, though, by just pointing out to you, you did it in 5 moves. This is Bayes optimal. It cannot be improved on. So how did you do it? It's a really deep question. It is mathematically impossible for you to do, I put 6 there in the font, hope you were bright. I didn't realise you'd actually get down to 5. How did you do that? There is an answer.
I think we may have scanned the whole thing a little bit more at the first trial. I don't think that there were only 5 trials.
That's certainly true, but I hadn't given you the outcome, so you couldn't deduce. There was no information that would resolve any uncertainty. There were patterns that, well, that's, yeah, I think that's half the answer. But it's not the fact that you knew the answer in advance, because I didn't give you the, it was the 5th answer I gave you that the rule was actually articulated exactly as it was. But the pattern, the notion of pattern structure. So I think that's where the clue is. So how on earth can somebody beat Bayes? This agent knew exactly what you knew, and yet it took 12 moves before it was 100% in terms of its performance and confidence. Pursue the pattern idea. Exactly, exactly. The very fact you knew there was a rule narrows the hypothesis space down enormously. And I didn't tell my agent there was a rule in play. So just knowing there is a rule in play enables you to clear the table of all sorts of implausible configurations of that A matrix. So to think about what is a rule. A rule is, well, if A, then B. But it's only B. It's not A, B, C, or D. That means that for any, if you like, column of that A matrix, for any combination or mixture of hidden states of the world, that means one and only one of the outcomes can have a value 1, and the rest are 0. Just that, you don't know which one it is, but the fact you know that there has to be this unique low entropy contingency or likelihood mapping means you can exclude a whole universe of A matrices. What does that mean from the point of view of Bayesian inference? Well, what it means is, instead of having to explore 10 to the 12, 10 to the 30 possible configurations of the A matrix, there is a small number, that in fact there are only about 36, that the agent could plausibly have gone through. So basically, an idea. If that, then that, then that. Does that work? No, it doesn't. Let's try this one. If that, then that, then that. Because this one is actually selected from a countably small number of plausible hypotheses that you have to wait until it comes into mind. But once you've got it, you can evaluate that hypothesis, and if it's consistent with the evidence, you've won. And if it's not, you just keep on going till the end. So what you've got is basically, because the very fact that you knew what a rule is, means you can reason beyond the evidence at hand. And you can be ampliative in your abduction. And that's the key thing that my agent didn't have, which you did have. But now, in all fairness, I'm now going to give my agent that knowledge. And let's see how it does. Let's see if it can compete with you. And the way I'm going to do that is through something. This is a technical thing for those people who know about it. It's called Bayesian model reduction. It's a really trivial and simple way of comparing the evidence for different models, hypotheses, based upon evidence that has already been accumulated. And in this instance, it actually unpacks into a very simple equation, which means that I can basically set my A matrix connections to 0 if there's not enough evidence for them in relation to my for any one set of hypotheses that have to conform to this. There's a rule there. So at least one of the columns should have zeros everywhere apart from 1 somewhere. And I can write those down, and I can test the evidence for all of these given the data to hand, and I can switch off redundant connections if my model provides greater evidence than before. And this is the result of that. Here's this A matrix. This is the true value with these nice structures for rule left and rule right. This is how we started with. These are the accumulated evidence on that naive Bayes optimal model that didn't know that there were rules, what a rule was. And this is what happens when I do my Bayesian model reduction. If I tell it, well, actually there's a rule there. So only a small set of A matrices are going to be plausible a priori. And of course, it can find much more efficiently the true structure. How efficient is that? Well, first of all, I'm just going to simulate thinking about all the evidence to date, shortly before, after 12 moves, and I'm going to pretend that's like sleeping. It's basically rehearsing everything you've learned and eliminating redundant connections or synapses to reduce your model, to get a simpler explanation which has a higher evidence for the data that you've accumulated during the day. And when we do that, we actually see, if you like, a categorical increase in performance in terms of free energy and confidence with sleep relative to without sleep. So there's a measurable behavioural improvement if you allow this little agent to take a nap after it's learned enough to make the Bayesian model comparison or reduction a useful thing. A much more interesting implementation of this this simplification, this Bayesian model reduction, is to let it think about its move after every move, after every trial. Just be a little bit more mindful about it. Just reflect on what happened. Say, well, perhaps I can get rid of this parameter in the A matrix if it's more like a rule than the one with the parameter in the A matrix. And if I do that, and I simulate this many, many, many times, I get this result down here. Ignore these, they're not very interesting. The key point I wanted to make is down here. So these are 64 subjects. The first one is exactly what the game that you played with a, well, in fact, it's not actually, because this one was a little bit, right, sorry, no, this is with the, with this prior, this hyper prior, if you like, that rules are in play. And happily, we now see that the median number of games these agents have to play before they discover the rule is actually 5. So we have an explanation as to why you were somehow magically being able to beat Bayes. The fact you knew there was a rule there, you knew there was a pattern there. You knew there was a structure that constrained all possible explanations for the contingencies, and you used that to just examine selectively and judiciously the particular hypotheses that you wanted to evaluate. And that's basically it. That's it. Thank you very much. I just want to thank my collaborators and thank you for your attention. Thank you.